Today, we will continue control the design, but for different dynamics. First, introduce the Euler-Lagrange systems. It's a general system that includes many different dynamics, like robot manipulators. It's one of. It's also Euler-Lagrange systems. Okay. So here. Then I will given a system, I will introduce the controller designs. And first, we will assume that the model knowledge is available. Okay. And after this, which will probably be next week, we will assume that the system parameters are unknown and you have to design the controller in different ways. Okay, so today the controller is designed with exact model knowledges. Okay, so consider Euler-Lagrange systems, and this dynamics is been described to. This dynamics is used to describe like robot manipulators. Okay, so in the robot manipulators, you have inertias on each link, and the links are connected by joint, right? And so by observe these equations, M you can consider as the mass of the system, or sometimes we call inertia. Okay. Q is the angle. Q double dot means the angular acceleration of a robot. G is the gravity. L is a constant. It's a non-constant that models the geometry of the link. Okay. And sine Q, which is the angle, and equal to tau, which is torque. So given, and torque represent the output of the motors. Okay, so the objective here is just the model, right? But next, for the controller design, the objective is to design this torque, which is considered as a control input, right? And you design torque to stabilize the system, or for the system to track a given trajectories. Okay. So in this case, what usually in the industry, what you want to do with this robot is you want to use the robot to track some desired trajectories, right? To do some automations in the factories. So Q, you want to design control input, which is the torque applied on the robot joint, and enable the Q, the angles, to track the given given trajectories, right? And remember here we assume exact model knowledge just for today's class. So M, L are non-constants. You know what is M and what is L. And Q and Q dot are measurable, right? You can measure the angle of the joint. Usually you use encoder as a sensor to measure the angle. And Q dots you can obtain by differentiate the angle. And you can do that because the Q in this case is measured by an encoder, which doesn't have noise, right? Encoder is a digital device. Usually it doesn't introduce noise. So maybe do the using numerical method to calculate the angular velocity is fine, okay? But the Q double dot is not measurable, which is usually the case, right? How can you imagine any sensor that can measure the angular acceleration? Usually not too much. right? So the most general way to measure the angle of the joint is by encoder N. So Q and Q dot is measurable. Okay, remember these assumptions. Okay, now, given this dynamics, usually we say this is a governing equation from dynamics. Okay, from your undergrad class dynamics, you can get these equations, right? And using this equation, you can obtain, usually in the control design class, we rewrite this system in this form, right? You put the state dynamics on the left hand side equal to some described by ODE, right? Okay. So now your states here, your control inputs here. So next, and again we assume model is exact model knowledge. Okay, and these states are measurable. Okay, Q is a state. So as I mentioned, the objective will be a tracking control. You want the robot manipulator and the end effector to track some desired trajectory, QD, right? So QD is predefined by user, right? If you want to pick, or in the car factory, you want the robot arm to follow some trajectory, do the paintings, right? You want the robot arm to follow some spatial trajectories. Those trajectories are described by this QD, which is a function of time, right? So this is predefined by user. And how the objective is how you can control Q, how you can design a controller that enable Q to track QD. In other words, to make sure the error will converge to 0, right? Before we always discuss X, but now since it's a tracking problem, there's no X anymore. The X is replaced by error signal. Okay. Any questions? So this is tracking problem, tracking control. And before it was regulation. Regulation means you want the state goes to 0. But here the state is tracking error. Okay. So assumption is the desired trajectory, the desired pose or the angle is known. Angular velocity is known. Desired angular acceleration is all, both are known and they are bounded. Okay. Makes sense, right? You don't want to design. You want to predefine some trajectory that its acceleration is infinity. That doesn't make sense, right? You are create a problem that you need to solve, right? So all these signals are bounded, and the objective is make sure this tracking error will be 0 as t equal to infinity, which is asymptotic tracking. Okay, usually before we say asymptotic stability, now we say asymptotic tracking because it's tracking control problem. Okay, so given this error signal, what you will do next before you design the controller is you will take the time derivative on the state, right, which is error. So you take the time derivative on E that obtains QD dot and minus Q dot. Okay, so that's fine. But the problem here is what? If you remember that if you just take one time derivative, the Q dot will pop out, right? But remember that control input tau is related to what? Q double dot, right? Because your torque the input of the torque will reflect on the angular acceleration, right? Torque controls angular acceleration, right? Torque doesn't control angular velocity. Okay, so remember in the previous slide, here, see, here's the torque, and there's an equal sign, equal to Q double dot. So torque controls the angular acceleration. Okay, so if you take only one time derivative, the control input will not appear here. Okay, that means your control input cannot be introduced. So we need to take one more time derivative, E double dot. That gives you QD double dot and Q double dot. And this Q double dot enable you to substitute the open loop dynamics, where right, you can substitute this Q double dot into here, and that means you can now see the control input torque, control input tau here. Okay. So all these are just preliminaries before we design the controllers. So usually the steps for designing the controller is, and stability analysis is, you need to define the open loop dynamics, right? Okay, and you will write down, rewrite this form to be Q double dot equal to something and plus torque. Okay, and next you design your controllers. Usually that consists of feed-forward terms, feedback terms. Okay, so feedback term is like, remember in the previous class we introduced minus K in the robust control. We say usually you have two terms, right? The first one is feedback term, second one is robust term, and this is a robust term. Although they have the same structure, right? Eventually it was designed as minus K2x, which is the same structure as this. But the functionality is different. This one is for feedback. This one is to deal with the disturbance or noises. Okay, so the functionality is different. And the reason we call it feedback is feedback term makes sure the system is closed and ensures stability. And this don't take care of the noises. So in your undergrad class, we have some reference signal here, right? Plus, minus. Remember we say it's maybe K, C, and G here, and this is a measurement. Okay, this is sensor measurement, and this K, this we call this is feedback term, right? Remember, right? Because it's minus here, and so, and we assume measurement usually we say is X, but in reality not necessarily, right? If measurement equals to X states, that means your measurement is the state, but that's not usually the case in reality. Okay, but anyway, here means that this is your control input, right? This is U. This is control input U, and U will equal to some minus Kx, and minus here. Okay, that's why it's called feedback control. It closes the loop and makes sure that this one will track this one. Okay, and for robust control, this term usually come into play when you have some disturbance come into here. That we call it theta UDIS. Okay, and this robust term will be considered in here, and it takes care of this term. Okay, so they have different functionalities. So is that clear? So we call this a feedback term. And here in this structure, feedback term in the controller, usually feedback term is required. And why here we put feed-forward term, but why here no feed-forward term? The reason is because it's a tracking control problem. Okay, it's a tracking control. It's not, here's regulation. Okay, you want, here the objective is you want s goes to 0. Here is you want for tracking control. One tracking error, which defined as qd minus q goes to 0. Okay, and here you just s go to 0, or maybe for easier to compare, q goes to 0. So they are different problems. Here's q go to 0. Here is q tracks qd, right? It's the same, right? 听懂吗? Okay. So why you need feed-forward here? In this case, because you are tracking some trajectories, like you are driving cars. So you use your eyes and your action, your controller, which is the steering angle, to follow the path, right? To follow the road, right? So in that case, what is feed-forward? Feed-forward is you use your sensor, your eyes, to measure the radius of the term, right? So you have forward knowledge, which you call forward control in here, okay? So whenever you are doing some tracking problem, you need to add feed-forward, and that will improve the tracking performance, okay? And here, there's no feed-forward because you are tracking a trajectory that is stationary, okay? 听懂吗? If you are tracking something that is not stationary, it's better to add feed-forward, okay? Feed-forward, okay. So what is feed-forward? You will see feed-forward in a few seconds. Maybe that's the problem, right? So next page, okay. So in the control design, this is controller design for tracking problems, okay. So we take a step forward. So this is feed-forward term. Remember, you put this term in the control. This term is associated with the trajectories, right? It's qd double dot. The information includes the desired trajectories. Desired trajectory means user defined. You need to give the controllers, to tell the controller, hey, I'm trying to go somewhere and you need to consider this so you have a higher performance. Like you drive the car, you need to know what's happening in front of you, right? And this feed-forward, forward and backward. Feedback means you are compensate something backwards. Okay, feedback. Back means it already happens. You have some difference in your. You have some difference of your state. You want it to go to 0, but it's not 0, so you compensate the non-zero term. Okay, 懂吗? Forward, feed-forward means you are compensate something happening forward. Okay, so you have previsions, what's going to happen, and you take before it happens. Okay, and so that makes sense, right? For the tracking problems, you are tracking some predefined trajectory. You need forward term and backward terms. Okay, so keep that in mind. You will understand gradually. So the procedure first, given the open loop dynamics, right? It takes some. You cook around the ODEs and get the different the ODE with states. And next, design the controller usually that consists of feed-forward term, feedback terms. And with the controller being designed, you can substitute back to the open loop dynamics. And that gives you the closed loop dynamics, right? Closed loop dynamics. You add the feedback. Now the system, the overall system is called closed loop dynamics. And that still can be described by an ODE, right? OK, 这样懂吗？懂不懂？ Okay, and next you select or you design the dipole function. They will be used to prove stability. So you design a dipole function, usually is PD and radially unbounded. And eventually you take this closed loop dynamics into the time derivative of the dipole function and do the analysis and see if V dot is negative or at least negative semi-definite, which shows it's stable, right? But if it's ND, it's asymptotically stable or tracking. Okay, so this is just the procedures. And next I will give you some design examples. Any questions here? You substitute control into here, control into the open loop dynamics, and you got closed loop dynamics. Right, because the control have feedback term. Once you substitute back to your dynamics, you can close the loop. Okay, so maybe we let's get into the examples, then it will make more sense. So basically, I design given the same dynamics, I design 3 examples. Okay, and the best one is upstream 3, but upstream 1 and 2 is just for education purpose. Okay, so because for upstream 1, usually you will consider to design your dipole function as this form, right? It's PD and it's RU. You are doing well. You are not doing anything wrong, right? But it doesn't work. Okay, designing this dipole function cannot be used to prove stability. Okay, why? So let's try. If you design this dipole function, next by following the step on the previous page, the next you need to do is take the time derivative, right? If you take time derivative of this, you got E M E dot. You got, because m is constant, right? It's not a function of time. So you take the time derivative. The only thing will change is e. Okay. And given this e dots, you can substitute the dynamics of e dots. And that's according to the definition. E dot is equal to QD dot minus Q dot. Okay, right? 对吧? So what's next? Nothing you can do. It's game over. Nothing you can do. Because Q dot controller happens in Q double dot, right? Q dot equal to So if you design this dipole function, if you try option 1, design this dipole function, okay, you just end up with this formulation, and nothing you can do further. Okay, so it cannot be used to analyze the stability. Okay, so let's try option 2. Now I added this term marked in red, okay, and by taking the time derivative, now you have E double dot pop out, right? E double dot, they will help, because E double dot means E is defined as QD minus Q. E dot is equal to QD dot E double dot is equal QD bar bar Q double dot. Okay. You need Q double dot because your dynamics comes into here. Your control input is controlling the second time derivative. So next, what you will do is you want V dot to be negative definitely, right? But how? How you can turn this structure into this structure? The only thing you can do is design this torque, design this control input, design your controllers, and that can maybe cancel out some terms and make this term looks like this. Okay. But there's a problem for coming from 5 to 6. There's a problem because these terms and the second terms are independent. Okay. So that means by design these controllers, no matter how you design, let's try this. You take time derivative. You got E M E dot plus E dot M E double dot. You substitute your dynamics. You got E M. This is Q D dot minus Q dot plus E dot M Q D double dot minus Q double dot, and you can substitute the control into here. That gives you minus Q dot minus this, right? Minus on the right hand side. This term Q okay. So now design next. Design tau, okay? Because nothing you can change other than tau, right? Tau is the controller. You can design whatever you want to put in the control. So how will you design tau? For me, I was trying to okay. I will design tau, okay. Let's try to use this tau to cancel this term, okay. Cancel this term. How? You can design tau as m and same as this term, right? Minus GL sine Q. Right? If you substitute this into here, this m will cancel out this m. That gives you everything in the bracket, right? And this from here will cancel this, right? 对吧? Okay. So this power be gone. Okay. 对吗？还是差一个负号 ？Okay. So plus. 你们果然喜欢计算，对不对？那举个例子。好。Then next cancel out this. Okay. Can you? How? Plus or minus? Plus m, right? Because there's an m here, and q d dot, right? 对吧? So if you substitute this into here, this term will be gone, right? 对不对? Okay? So you don't want the whole term to be gone. You want to keep, for ND, right? You want to at least create these kind of terms, right? Because it's essential. Both terms are essential to show it's ND, right? So you want to reproduce these terms. How? Because it's positive, right? So you can, so our design, again, m here, minus here, right? So, and you have e dot here, so you need to, we want e dot squared, so we need to put one more e dot, right? So if you substitute this into here, you got minus e dot times plus e dot m. They will give you minus e dot square m, right? So this is same, like the m is like k here because both are positive, right? M is always positive, okay? There's no negative inertia, okay? So this term is done. It's done, right? Okay? But how can you design using similar structures to cancel out this term and create the first term here? Can you? No, right? Because there's a coefficient here, e dot here. No matter what you design tau, e dot will still be there, right? So there's no way you can produce the first term here that is essential to conclude v dot is negative definite. Okay? 听懂吗? So what's the problem with this approach? Can you attribute the reason? Can you attribute the variable of designing this controller to the controller design tau here? No, right? You can attribute the controller design because e dot always there, right? There's nothing you can do. So basically, what is the problem is this Dearborn function. Okay, you should not design this structure. What's the correct approach? What's the right approach? Which is option 3. Okay, we mentioned option 1, right? But we did not describe going into detail too much because it's just stop here. Okay, nothing you can do. So option 2 have some problems because the best you can prove is NSD. The first term is missing, right? So next, option 3. Option 3, we try this 1/2 and mr squared. Okay, we define a signal called R, which is filter tracking error. Okay, compared to here, we don't use E squared and E dot squared because they are independent. And independent of these two signals is the problem, right? As you can see here, it's always here. You cannot reproduce some good terms here. So we try this structure. But what is R? R is the filter tracking error. So we need to reintroduce filter tracking error first. So what is filter tracking error? It's defined as R equal to E dot plus alpha E. Alpha is any positive constant. Okay. And you can consider it's a control gain. But it's not the only control gain. Okay, you can consider it's control gain. but not the only one, okay? Not the only one. So here we want to show that some property of R. So if R is bounded and R approaching 0 as t go to infinity, that implies both E and eta will approaching 0. Okay. This property is required because if you use R, as we mentioned, if you use R in the Debye function to replace E and E dot, right? If you use R to replace both, and eventually the best you can show is ND, right? So given this, you can conclude R will goes to 0, right? But what we want is E goes to 0, right? For a tracking control, we want E goes to 0. So how can you infer from R goes to 0 to E goes to 0? How is, so we need to prove that, right? If R goes to 0 as t goes to infinity, by designing this structure, you can ensure that R goes to 0 and both signals will go to 0, okay? And here's the proof. So if this is correct, that means if R goes to 0, both signals will go to 0, then you can design this V3 as a Debye function, right? Because this only proof R will go to 0, right? PD and it's ND, which means R goes to 0. But R goes to 0, with that properties, you can show that E goes to 0 too. So if this is okay, we can now design this Debye function. Okay, take the time derivative. Okay, R dot is E double dot plus alpha, which is constant, and E dot. Okay, and here with E double dot, you can substitute Euler-dynamics. Okay. Okay. R dot is E double dot plus alpha E dot, right? And it implies R, and this gives you QD double dot minus Q double dot plus alpha E dot. Okay, and here is the signal that associated with control input, right? You can substitute Q double dot on Q double dot equal to minus GL. Okay. So with that, you have Rm QD double dot, and you substitute this into Q double dot here. That give you minus GL sine Q plus tau M plus alpha E dot. Okay. So this becomes this, okay? Exactly the same. So now you can design this tau, such that V dot, okay, this is V dot. V dot will be negative, definite. Okay. So how? So the way to design this tau is this. Okay. See why? Because let's take term by term. Okay. So what's this? This equal to QD plus GL sine Q, right? So in your tau, you can put the m and m times this term, the minus m times this term, right? Okay, and let's cancel all these terms. Okay. Okay. But you need this, right? You need this to show negative definite. So you need to recreate this term. You have one r here, you need to create another r, which is minus r. And m times m. Because you have m here, minus r. Okay. And if you want to put a control gain, so you put minus kr. So this is mkr, which is this term. Okay. So here is negative. Sorry, negative. So you don't need negative here. You don't need negative here. Okay. So now this cancel out, and we have minus KMR here. Okay. But this term is still there, right? We need to cancel out this term. So how do you design the term here to cancel out this term? How? You add this term in the control, right? So you add exactly the same term, alpha E dot and m here, because you have divided by m. Okay? Is that clear? 听懂吗？如果你 miss 掉 something， 你回去看 video。OK？ 所以 procedure 就是这样。So this give you v dot is negative definite, and you can show r goes to 0 as t equal to infinity. And that implies from the property in the previous slide, you can show both signal go to 0. Okay, so not only you can track the trajectories, the velocity will also match with the user predefined trajectory. Okay.